Hello again to your channel of Math and Engineering Made Easy. Today, I'm going to give the second session of Pappus Theorem. Before we start, let's take, uh, we can have half a circle or a quadrant. It really doesn't matter. Let me tell you, suppose I want to find the centroid of a quadrant, just one quadrant, okay? So this quadrant, it doesn't matter if you rotate it about the x or the y because it's symmetric. So it's x bar and y bar. So if that's the origin, this is x bar and y bar, they should be equal, right? Because the shape is symmetric. And I want to find x bar and y bar. So rotating it about the x or the y doesn't matter. So let's rotate about the x this time, since last time we were rotating about the y. I know the area of this shape, right? If this is R, then the area here is pi r squared over 4 because it's a quadrant, a quarter of a circle, right? And if the centroid is here, I'm going to call it y bar, right? I don't know it, but when I rotate it, the volume would be pi r squared over 4 times 2 pi y bar. But I don't know y bar. But what do I know? I know that if this quadrant rotates one full turn about the x-axis, I will get a solid hemisphere. The area, oh, I'm sorry, the volume of a sphere is 4/3 pi r cubed. So the area of a hemisphere is 2/3 pi r cubed. Now, equating and solving for y bar, we will get the following. I can cancel pi with pi. R squared with the cube, leave that as R. 2 and 2. And then multiply both sides by 4 over pi, by 4 over pi. These cancel. And I get y bar, which is the centroid, which is the same as x bar, because of symmetry, equals 4r over 3 pi. And that's how you can find the centroid of a quadrant or a semicircle. If it's a semicircle, the x bar would still be 4r over 3 pi. The y bar, of course, would be 0 because the centroid would be on the x-axis. And if I make half a circle like that, the x bar would be 0 on the y-axis, but the y bar would be the same. So that was like an extension to what we did last time. The second part of Pappus theorem says you don't have to rotate an area. You can rotate something like a wire, like a line. And this line will generate a surface area. And the idea is exactly the same. Let me show you a very simple example, extremely simple. Here is my x and y. I'm not going to waste your time by drawing it like with a ruler or anything. I'm going to say I have a line here of length L, and it's at a distance of R. Okay, where is the centroid of this line? Yes, it is at L over 2 here, right? At a distance of R also from the y-axis. So if I rotate this line about the x-axis, it will, excuse me, it will generate the surface area of a cylinder. Yes, without the top and the bottom, because I didn't measure R and R. It's just going to generate, oops, it's not drawn properly, but it will generate this cylinder. I know the surface area of the cylinder, right? So let's see if we get it by using, instead of area, I use length. And instead of volume, I will have the surface area. So the surface area equals the length times the distance traveled by the centroid. The distance traveled by the centroid is 2 pi r because it's r away. We know that the surface area of a cylinder is 2 pi r h, where h is the height. In this case, it is L. Wow. So it also works with lines and surface areas, not just areas and solid volumes. Nice. So now, this is a short session because just it's an extension of what we did. I didn't want the previous one to be lengthy. This time I say, take this a quarter of a circle, this quadrant, but this quadrant is not a plate like before, so this is not an area. No, it's just this line, this wire. I have this wire, and I will rotate it about the y-axis or the x-axis for that matter. X, y, and y bar, as we said, they would be equal because of symmetry. But now this is a wire, and I want to see where the centroid is. X bar equals Y bar equals. We said the length of the wire is a quarter of the perimeter. The perimeter of the circle is 2 pi r. So this distance is 2 pi r over 4, right? That's the length. If I multiply it by 2 pi x bar or 2 pi y bar, it will generate half a sphere, a hemisphere, but it generates the surface area of a hemisphere. I know that the surface area of a sphere is 4 pi r square, so that would be 2 pi r square, right? Hemisphere. Simplifying, 2 pi and 2 pi cancel, r with the square cancel, dividing, or if I multiply by 4 over 2 pi, do we have... So this will give me x bar or y bar, and this would be the 4 and the 2 would make 2r over pi. And that is the centroid of this shape. Some people always come to me and say, how is the centroid out of, it's not on the line? Of course it's not. And so what? Have you ever seen like lights like that are circular? Right? You have a light fixture that is circular, right? Where is the centroid of that shape? Yes, it is the center. Meaning I have to connect it maybe by 3 or 4 wires. And if these have the same length, meaning I'm exactly at the center, and I hold this light fixture, it would remain horizontal, meaning I'm carrying it from the centroid. The centroid does not need to be on the shape itself, right? Yes, for the straight line, it was in the middle, but if it's curved line, of course, it cannot be anywhere here. It has to be somewhere outside of the shape, and that's perfectly fine. As long as between so it cannot be here, for example, okay? But anyway, that's a very minor thing, but you have to understand that it's fine, especially for void members, to have the centroid in a void. That's no big deal. Okay, I hope this was an easy one, and it shows you the power of Pappus Theorem, who existed like before Christ, and how advanced Greek were in math. I hope you like this one and it may help you in some of your work or some of your courses. Again, you don't need integration in cases like that if you know two of the three, length and centroid and area, or area, centroid, and volume. Okay, thank you very much for your time. Hope to see you soon. Have a great day.